Good evening and welcome to the Longmont Museum. We're a center for culture in northern Colorado where people of all ages explore history, experience art, and discover new ideas through dynamic programs, exhibitions, and events. My name's Justin Veach. I'm the manager of the museum's Stewart Auditorium, and I curate public programs for the museum as well. Thanks for being here tonight. I'd like to thank all the folks who make our programs possible, the Scientific and Cultural Facilities District, the Stewart Family Foundation, the Friends of the Longmont Museum, our many museum donors, and of course, our museum members. We have any museum members with us this evening? Hey, thank you, members. We simply can't do all that we do without you, so thank you. Tonight's program is being offered as part of our, I should also thank our media sponsor, the mighty KGNU Community Radio out of Boulder, just down the road, and the Longmont Leader, your source for online news here in Longmont. Tonight's program is being offered as part of the National Center for Atmospheric Research's Explorer Series. The series brings world-class science directly to the public through presentations, videos, and participatory science initiatives led by their research scientists. Explorer Series programs touch on pivotal areas of NCAR research such as climate science, natural disasters, ocean currents, air pollution, and the behavior of our sun. Some presentations deal with front-range atmospheric issues that affect Colorado residents directly, like tornadoes, while others focus on global priorities that influence national and international decision-making, like climate forecasting. This evening's program, A New Era of Extreme Weather Impacts, will explore what we know about our changing extreme weather and how scientists study these changes, as well as showcase how ongoing partnerships between science and industry are creating new, usable science and accelerating scientific discovery. It's my pleasure to introduce this evening's speaker, Dr. James Doan, Senior Willis Fellow and Deputy Director of the Capacity Center for Climate and Weather Extremes at NCAR's Mesoscale and Microscale Meteorology Lab. Dr. Doan works with stakeholders from the energy, water, and insurance sectors to understand our changing extreme weather and climate events, as well as their impacts. Examples of recent work include assessing future hurricane impacts on the offshore energy industry, exploring the value of multi-year climate predictions for water resource and flood risk management, and understanding the residential losses during hurricanes. He recently testified before the U.S. House Committee on Science, Space, and Technology on extreme weather and climate change. Dr. Doan received his PhD in meteorology from the University of Reading, UK, and has been with NCAR for 15 years. He also lives in Longmont, of course. Ladies and gentlemen, please join me in welcoming Dr. James Doan to the Longmont Museum.
Well, thank you for that kind introduction, and yeah, so great to see many here tonight. Thanks everyone for coming out on what is a rather dreary Longmont day. So yeah, welcome. So I'm a scientist at the National Center for Atmospheric Research. I'm also a Willis Research Fellow. So Willis are a global reinsurance broker. So today I'm going to say a bit about how I work with the insurance sector to make society more resilient to extreme weather. So overall, I'm going to motivate that we're in a new era of extreme weather impacts. There we go. So I'm going to kick things off with a couple of examples of recent extreme events. And unfortunately, we have many to choose from. The first one I'm going to start with is the severe heat in the Pacific Northwest last June and July. Many of you will probably remember this. So what you're looking at here is the annual cycle of temperature in the town of Lytton, British Columbia, just north of the US border. The black lines are historical years, and the green is the average historical annual temperature cycle. Now, the red line is what happened last year, and you can see it followed history very well until we got to June, when it really spiked upwards, and it hit 121 Fahrenheit. Now, this broke the national record for Canada, and it broke it by 8 degrees Fahrenheit, which was amazing. Normally, when a national record is broken, it's only broken by about 1 or 2 degrees, so 8 degrees is almost unprecedented. And just to put this in context, the typical average high on that day is 77 Fahrenheit, so this was 44 Fahrenheit above normal. So just to bring this back home, in Longmont, on that day, a typical average high is about 86. So if you add 44 degrees, you're going to get 130 degrees. So that would be astonishing if we had a June day of 130 degrees in Longmont. I'm not saying that is ever physically possible, but it gives you an idea of how unusual this event was. And unfortunately, about 800 people, at least 800 people lost their lives in this event in the Pacific Northwest broader region. And unfortunately, the day after, this town burnt to the ground. So here's what we call a pyrocumulonimbus. So you probably heard that thunderstorms are referred to as cumulonimbus clouds, but this is a fire-induced thunderstorm, so we call it a pyrocumulonimbus. So this is a hybrid smoke plume combined with a thunderstorm. And this thunderstorm itself triggered hundreds of lightning strikes that most likely triggered more wildfires. So this was an absolute monster, and the fire probably wouldn't have burned as intensely or moved as fast if it hadn't been for the record heat the preceding days. And of course, talking about wildfire, we have to mention our own tragic event, very recent history of the Marshall Fire. So some of you may have been directly impacted by this event or know people who were impacted. A real tragedy, one of the worst wildfire events in state history. And what shocked me about this event was how the wildfire just burned through the suburbs. I always thought that wildfire risk was confined to, say, the western regions of Boulder, against the foothills, but this event just tore through the suburbs on the plains. So it switched from an open grass fire to an urban firestorm where the fuel was the homes. It was no longer the open vegetation. So what caused this fire? Well, there's no single event. It was actually a convergence of many events. If you remember, we had the extreme winds, so those are common around here, but on that day they were exceeded 100 miles an hour. The 6-month period preceding the event was the warmest on record for that period, and it was one of the driest. If you remember, there was hardly any snow. I don't think there was any snow in Longmont, at least, until the day after. And we've had expansion of the suburbs across the plains. So those 3 factors combined to produce this devastating event. So I think this was really a wake-up call to improve how we build our homes to become more fire resistant. Okay, so I'm sure many of you have experienced other extreme weather, and maybe in the Q&A you can share some of your experiences of extreme weather you've experienced, not just in Colorado, but maybe in your prior states that you've lived in or on your travels. Okay, so I just wanted to say a bit about myself and introduce myself before I dig into the science. So why am I here? Why am I interested in extreme weather? Well, I've always been a bit of a weather nerd, or weather geek, and growing up in the UK, I was watching the weather forecast. This was before smartphones. I had to wait for the weather forecast on the TV. And this guy here, Rob McElwee, he didn't just present the weather, he added some science in. And he was talking about these mathematical equations that he uses to predict the weather. And I was amazed. How can you use just an equation to predict a thunderstorm? I'm still amazed by it today, even though that's what I do for a living, and I'll explain more about that. And I grew up in York, in northern England, so our extreme weather there was flood. So here's an image of my hometown flooding. This pub here, it floods every year, and it's amazing that as soon as the water recedes, the pub opens up again, because it's well adapted. That's a good climate adaptation. And they have markings on the wall for the flood levels. And interestingly, the most recent floods are the highest markings. So something's changing. Okay, so I've always been curious about the weather. So some questions that I've always asked is, for example, here's a tornado in the hills near where I live, or where I grew up. This is a British tornado. It's rather benign. It just kind of disturbed the sheep, not like the devastating ones you get here. But I like to ask questions. Why does it look like it looks? Why did it happen then? Why did it happen that day? And will there be more of them? So I still ask those kind of questions today about extreme weather around the world. Okay, there we go. And so in 2004, after I completed my PhD at the University of Reading, I came over to work at the National Centre for Atmospheric Research to see some real weather. You have all the most interesting weather. So let me say a bit about what we do at NCAR. Many of you might be familiar already, but let me just review. So we're in the business of advancing our fundamental understanding of the Earth-Sun system. We also support the US university research, so we have facilities like supercomputers that we maintain for university research. Perhaps most importantly, we extend our scientific discoveries to society. So I'll give some examples about how we do that. And we also recognize that good science can only be done if everyone's voices are at the table, so we strive to promote a diverse and inclusive workforce. Okay, so I mentioned supercomputers, so I'm going to come back to this notion of using mathematical equations to predict the weather. And that's basically what our weather and climate models are based on, these equations of the atmosphere. We have equations for wind and ocean currents and sunlight and snowpack, and these all work together, and we can predict the state of the weather forwards in time. Now we have a new supercomputer that we call Deratio. Some of you may be familiar with that term. It's a term for a specific type of thunderstorm that we get very occasionally, maybe once a year, once every 2 years across the Midwest. It's a very large linear thunderstorm. It's probably about 1 or 2 states long, and it propagates right across the Midwest over about 18 hours and produces, say, 100-mile-an-hour winds. And so this was actually named by a school kid in Riverton, Wyoming. So we had a competition, and this kid won. So I hope he comes to work at NCAR later. Now, unfortunately, we don't yet have this supercomputer. I think there's a chip shortage, so it's probably stuck off the coast of LA, I think, at the moment. Okay, now we don't just simulate the weather, we observe it. And some examples of ways we observe the weather is Gulfstream 5. So this is our Hyper aircraft that goes up to about 55,000 feet. I just heard that might not be as high as some aircraft you're more familiar with. But it goes up above the weather to look down, and it has a range of about 11,000 kilometers, so it can really get a broad, expansive view of what's going on. And we also have satellites. We were involved in launching a suite of satellites we call Cosmic 2. So it's not just one, there's many of these circumnavigating the globe, and they talk to each other. And they see the temperature and the moisture between each other and give that information back to our weather forecast models. And we've shown that that kind of data improves weather forecasts, and particularly for hurricane forecasts, say. So we're gathering data in real time to improve our predictive capacity. Okay, I have to show this. This is close to my heart, that we do the highest quality science. Now, as scientists, our currency is publication. So we do research and publish our findings in journals, and then we measure how popular those publications are. And that's measured by how often other scientists refer to them. And that's what you see ranked in this table here. So you see that NCAR's science is most popular and is more popular than even Harvard or Princeton, and pleasingly, it's more popular than UC Boulder. So we win that one. We've also developed the most widely used weather research technology. So our weather forecast model is the most widely used on Earth. It's used in about every country, which is an amazing feat. Okay, so interspersed in these this hour or so, I'm going to give you some multiple choice questions, just to keep you on your toes. So what do you think weather and climate scientists such as myself do all day? So it's multiple choice, you have to shout out your answer. So let's see if this works. Well, don't shout out yet. I don't. You might get the wrong answer. Okay, here we go. Okay, someone did shout out all of the above, so yes, that's the correct answer. And we do more than this, which I'll say in the next slide. So I just wanted to describe what my job is, so you have a flavor of what I do. My job description is basically to discover new and useful things about weather and climate. So I think that's pretty cool. It makes me get out of bed in the morning. It's amazing that I can discover things that no one in the history of humanity has ever known before. So I love doing this kind of work. That's on a good day. So let's see. I think this is giving up. Here we go. So the way I make new discoveries is to develop new research ideas and influence people to fund it. So it's a very competitive field to be in. I have to be stronger than my competitors. On to the next one. I collaborate with insurance industry colleagues, and I'll say more about how I do that. I also communicate my scientific findings and invite criticism. So you might hear scientists arguing a lot, and this is how we make progress, but we like to find holes in other people's work. So I also critically review the work of others. Okay, so I started work at NCAR in 2004. So a lot's happened since 2004. What's relevant this evening is that greenhouse gases have increased. They've been increasing for decades, and you can see in this figure here, this is a time history over the past 35 years or so of our rising carbon dioxide globally. So in 2004, when I started, it was at 375 parts per million. It's now at 419 parts per million today. And of course, carbon dioxide is not our only greenhouse gas. We have methane, and that's been on a rising trajectory. So in 2004, it's at 1760 parts per billion. It's now up to 1909. So this is a pervasive increase in concentration. And why is that important? Well, just to review the greenhouse effect, we know that the sun fuels our weather and climate. So the sun is hot, it has a temperature, it emits heat radiation. Some of that is absorbed by Earth. So Earth now has a temperature, it itself emits heat radiation, but Earth has an atmosphere, so some of that heat radiation is trapped by our atmosphere that contains greenhouse gases, and it re-radiates that heat back down to the Earth's surface. So that heat coming from the sun is trapped within our atmosphere. So this is actually a good thing. We need that heat, because without any greenhouse gases, the average global temperature would be 1 Fahrenheit. But recent climate with the greenhouse effect is about 60 Fahrenheit, a lot more comfortable. But of course, too much greenhouse gas is bad. And this is the consequence of too much greenhouse gas, that the atmosphere is trapping too much heat. The blanket is getting thicker and thicker. So this is a measure of global temperature over the past 40 years or so, relative to some average in the middle of this period. So since I started work at NCAR in 2004, the Earth has warmed almost about 1 Fahrenheit. Now, the Earth has not just warmed, the atmosphere has become more moisture-laden. So the atmosphere is more sticky, there's a lot more moisture, so it's warmer and more humid. So it's no surprise that the weather events that circulate in this warmer and more humid air have changed. And I'll see how that's happened. Now, this greenhouse effect is nothing new. In fact, we've known about it for over 160 years. So this New Yorker, Eunice Newton-Foote, was the first person to identify the greenhouse effect. So she put forward this paper called Circumstances Affecting the Heat of the Sun's Rays back in 1856. And she conducted a cool experiment where she lined up glass bottles in the sunshine and filled the bottles with different gases and had a thermometer in each bottle. And surprise, surprise, the bottle filled with carbon dioxide warmed more than the other bottles. So it's a remarkable piercing insight there. And then this guy, a Swedish physicist, actually quantified the warming of Earth's surface through the doubling of carbon dioxide, and this was back in 1896. And these estimates of, say, 10 Fahrenheit are still pretty accurate today. And it's thought that this Svante Arrhenius is an ancestor of Greta Thunberg, so it runs in the family. Now, whenever I talk about climate change, I like to put things in the long history context. So now we're not just looking at the past 100 years, we're looking at the past 400,000 years. So now we're looking at ice ages and interglacial periods. So the red line is a measure of Earth's temperature. So you can see for the most of the part, it's been quite low. And those are the ice ages. But every 100,000 years or so, we have this interglacial period. And we're in one of those interglacial periods right now. Now, the blue line is carbon dioxide concentration. And you can see how closely they've co-varied over the past 400,000 years. And now suddenly we're way up at 419 parts per million, the highest it's been in a very long time. So what do you think the red line is going to do? And sure enough, it is going up. So of course, today is St. Patrick's Day, so we have to show some Irish data. So here you're looking at a history of the temperature in Ireland over the past 100 years or so. The bluer colors, the cooler the temperature, the redder colors, the warmer. So you can see we've transitioned from more blue on the left to red on the right, where we are today. In addition, there's lots of variability. We see some red bars on the left and some blue bars on the right, so that's climate variability. But overall, you can see there's a trend, a climate trend or climate change to this warmer world. And you can choose any country you like. You can go to, if you Google show your stripes, you can plug in your location and look at how these stripes have changed for your location. And these have gone viral, so if you have a Tesla, you can color it. Okay, so now I've said a lot about climate and weather, so let's just think about exactly what the difference is. I like to use this analogy that climate is your wardrobe and weather is what you're wearing today. So every morning when you get up, you open your wardrobe and decide what to wear. So you have a choice. So the weather also has a choice what to choose for that day's weather from the climate. Now, climate, like your wardrobe, changes. So if you get rid of some old clothes, take them to Goodwill, maybe buy some new ones, now you've got a new wardrobe, a new selection to choose from, and so that's much like climate change. Now we've got some new weather events that we can select from. The scary thing is that the weather we've experienced probably hasn't selected from everything that's in the climate wardrobe today, so we need to try and figure out what's in that wardrobe. Okay, so sure, we're going to switch over to extreme weather now. So what's been happening over the past 40 years? Here's a time series of the number of extreme weather events globally. Let's just look at this orange line at the top. The other lines are just categorized by different types. But the orange line has the numbers of global events have doubled in the past 40 years. Not only that, the costs of these events has also risen. So the blue line is global total economic losses from weather events. The red line is the insured component. So both of them have been rising. Not only that, they've become more volatile. Now, I want to point out this event here in 1992. So does anyone remember what happened in 1992? It was a disaster for a certain state in the US. I hear a hurricane, Sandy, any other hurricanes? Yeah, I think I heard Andrew, yeah. So Hurricane Andrew devastated South Miami in 1992. It was a Category 5 at landfall. And this was, you can see, it's caused losses much higher than anything in recorded history before that. So I'm going to return to that near the end of the talk. Okay, so we're now on to our second quiz, multiple choice. So why do we think extreme weather is becoming more costly? Let's see if it works this time. So we've got A, inflation, B, climate change, C, population increase, or D, all of the above. Oh yeah, you're a good crowd, yeah. You all got it right, it's D, all of the above. And actually there's a lot more factors involved. These are some of the main ones. So let's see which state has been experiencing the most losses over the past 40 years. So the darker the colors, the higher the losses. So this is cumulative losses over 40 years from any weather event. You can see the hotspots along the Gulf Coast there, also California and New York. So these events experience extreme weather. They're also highly populated and some of the wealthiest states. Okay, this is the final quiz, so I don't want to tire you all out. But, so what type of weather do you think is most costly? And this one tricked me. So we've got A, winter weather, B, flooding, C, hurricane, D, drought/wildfire. Oh, that's it. I hear lots of D's for drought and wildfire. Well, let's see. Let's see. Oh, no, there was one more, sorry. Clearly, that's not the answer. Severe thunderstorm is not the most expensive. Okay, so at the bottom of the ranking is winter storm and freeze, so that's produced up to $150 billion of losses over the past 40 years. This is all according to NOAA data. The next one, we have flooding. I thought flooding was going to be at the top, but I think it will rise to the top maybe in the future. Next up, we have severe thunderstorms. So here I'm talking about straight line winds and tornadoes. And then next one, we have drought and wildfire. This is actually rapidly becoming one of the dominant causes of losses. Wildfires are becoming more intense and burning greater area than they ever have done. And then at the top, of course, is hurricane with $1 trillion plus over the past 40 years. So in total, the US has lost probably $2 trillion of losses now over 40 years. So hopefully I've motivated that we're in a new era of extreme weather impacts. So the weather events themselves have changed, but so have we. So I'd like to illustrate this with Hurricane Ida last summer. This made landfall here on the Gulf Coast and then caused the flooding in New York, you might remember. Now, it's likely that the winds of Ida were stronger than they otherwise would be without the warming we've experienced over the past 30, 40 years. It's likely that the rainfall was also more intense than it otherwise would have been. But look at our population in these nightlights. So our population has also been rising, and there's more people, and people have more stuff than they used to. So what of climate change and all this? Well, we can think of climate change as a pervasive and growing risk multiplier. So the risk was always there. We've always been impacted by these events, but they're now stronger in certain respects than they otherwise were due to climate change. Okay, so I'm going to outline some ways that extreme weather has been affected by climate change. Before I do, let me just review how we know this, and that's through our weather and climate models. So let me just run through how these work. I think I alluded to it earlier, but we have equations, physical equations that tell us about the winds, the ocean currents, the sunlight, rainfall, and then we take the Earth's atmosphere and put it onto a grid. You see all these tiles, and this model happens to be hexagonal tiles. So each tile has all these equations, and then we look outside the window and take a snapshot of what's actually going on. We observe it through our aircraft and weather balloons, and feed all that data into this model, and then run it forwards in time. So these equations tell us what's going to happen 1 minute from now, an hour from now, a day, a week, a year, 100 years from now. And the smaller we make these tiles, the more detailed we can make the predictions. And we can make these tiles so small that we can depict things such as a hurricane. So this is actually a simulated hurricane. It looks pretty much like the real thing. So it still blows me away that this is just mathematical equations, but somehow we get something that looks like a hurricane. And we can run these models for hundreds of years and build up statistics of hurricanes. And we can look at how they might change from today's world going out to the end of the century, say. So what are we finding? Well, we're finding that already in some regions we have detected an increase in hurricane rainfall, particularly in Texas. So in fact, NOAA recently quadrupled its estimate of extreme rainfall for Houston. It kept receiving its 100-year flood every year. So it was time for a change. And our models show that this precipitation is likely to become more intense in the future. It's also likely that, I should caveat, I'm talking about hurricanes because that's my specialty, but I'll say something about other phenomena in a few slides. It's likely that hurricane winds on average will increase. This is a picture of Mexico Beach after Hurricane Michael roared ashore in the Florida Panhandle. We've also seen higher storm surge. And in fact, we're very confident in this because just the fact that the seas have risen. So the seas have risen because the oceans have warmed and warmer air occupies a greater volume than, warmer water occupies a greater volume than cooler water. And also the melting of land ice, so there's just more water in the ocean. So how about would we expect there to be more or fewer hurricanes in the future? So would anyone like to hazard a guess? I hear lots of votes for more. We actually don't know. So 10 years ago, we thought there were going to be fewer, but more recent work suggests there might be more. So we had some convergence and consensus, but more recently, we're now questioning that. So there's still some fundamental things about extreme weather we just don't know. This is partly due to the fact that hurricanes are so rare. We don't have a large enough sample size, so it's not to say that we are seeing more or fewer, we just haven't detected it in the data we have available. So and we can do that by waiting a few years for more data and also simulating more years on our supercomputers. Okay, that was enough on hurricanes. What about other weather phenomena? So let's think about severe thunderstorms, say in the Midwest. So on the left is our simulation of the tracks of thunderstorms across the Midwest for a single year. And on the right is what actually happened for a single year. And overall, we get these statistics, the general regions of the storms and the general numbers, pretty good from these computer simulations. So what we can do, we can run this simulation not just 1 year, but hundreds of years. So what do we see? Well, if we run it for current climate, these are the tracks of severe thunderstorms that we get. And the tracks are colored by how heavy the rainfall is. So the darker the red, the heavier the rainfall. What about when we look into the future and we see more tracks and the deeper red color? So the rainfall is heavier. And in fact, we see 4 times the number of strong storms by the end of this century than we're seeing today. So this means that the strongest thunderstorm we experience in Longmont on average now, we'll see it 4 times every year in the future. So these are huge changes we're seeing. And it's because the atmosphere is warmer and there's more moisture to rain out. So there's not just more of them. Let's have a look at what they actually look like on a map. So this is an average rainfall map from a storm in today's climate, a thunderstorm. And the colors are the rainfall rate. And here's a similar map in the future. So you can see it's redder. So the rainfall rate has increased by 1/3. So it's coming down harder by 30%. And these storms are larger. So they're almost double the size. And so the increased intensity and the increase in the area or the footprint of these storms means that the actual rainfall, the water falling out of the sky, more than doubles by the end of the century for the strongest storm that we might see once a year. And these are not just small events. So let me show you a map this is the boroughs of New York. You can barely see Manhattan in there. So these are multi-catchment, multi-urban area events that could cause dangerous simultaneous flooding. And this is a problem because our cities' urban stormwater infrastructure was designed over 100 years ago. So they were designed for a climate that no longer exists. So I like to show this figure. This is down a street corner in downtown Pittsburgh, taken 100 years apart. So you can see lots of things have changed. The thing that hasn't changed is the size of this drain. Really, that drain should be about twice the size it is to prevent urban flash flooding to the extent it was prevented 100 years ago. Okay, so now back to wildfire. You probably read in the papers about these power shutoffs that the California utility is having to do to prevent wildfires. So the problem is that the transmission cables most of them are above ground, and when it's windy weather, it can knock these pylons down and trigger wildfires. So they take a preventative step and just turn off the power. This is a problem, of course, because we need power, and it becomes a problem if it happens more days than not. And so this was an interesting study that was conducted a couple of years ago. The height of the black bar is a measure of the number of people impacted by power shutoffs, and on the left is a typical year. On the right is a year of very dry autumn vegetation. And other work has shown that dry autumn vegetation is a signal or response to climate change. So it's likely with climate change, we're going to transition more to this higher bar and a greater number of people impacted by these power shutoffs. So it's a policy that needs reviewing. And sticking with California, of course, it's not just the dry extremes. California is prone to flood. Now, let me tell you about this flood that happened in 1862 in California. So this was a flood like nothing we've seen since. It flooded the entire Central Valley. It was basically 30 days of intense rainfall. You can see a depiction there in the San Francisco Chronicle of flooded downtown Sacramento. And so, is this likely to happen again, was the question. So it would be disastrous. There's probably almost $1 trillion of assets now in the floodplain of California. So any losses associated with this event will probably dwarf the losses that we see typically from a hurricane. And in fact, these two studies here quantified that this kind of flood is more likely than not to occur sometime in the next 40 years. So this is very alarming, and we really need to understand what this would look like and how it plays out. And in fact, the state of California is conducting a preparedness scenario where they get all the emergency managers involved and conduct a response scenario to try and better prepare for such an event. Okay, so this brings me back to insurance. Do you remember well, one of you said about Hurricane Andrew in 1992, so this really rocked the insurance industry. So prior to Andrew, no such event had been as disastrous. And so the insurance companies were just not ready for it, and many of them went under. They became insolvent. So this is not good for societal resilience to extreme events if your insurance provider cannot provide in an emergency. And the problem was that they were looking backwards in time to predict the future, whereas we've just discussed for the past 45 minutes that the future is not going to look like what we've experienced in the past. So now the world of insurance is now looking at these climate models, and they build their own climate models to try and predict what's going to happen in the future. So this is where my collaboration comes in with the insurance industry. So I'm part of what's known as the Willis Research Network. So this is a collaboration between the world of finance and climate research to benefit both, basically. So really to infuse and support insurance with the latest science, but also for me as a scientist to understand the vulnerabilities of society better and really direct my research in ways that can be usable. So I think I have after this slide, I have an example of how that works as we come to the end of the presentation. So if you imagine there's these two pillars here. On the left is insurance solutions to risk, to weather and climate risk. And on the right, we have climate science. So I work in this green collaborative space where we work together to transform both the science and the insurance practice. So in this sense, the science informs the insurance premiums and how the insurance is structured. And also the science is informed by the scales and the things that, or the weather phenomena that insurance is vulnerable to. Okay, remember I showed you this picture of the devastation wrought by Hurricane Michael in 2018 in the Florida Panhandle. It's interesting that many homes were flattened, but not this row. They somewhat survived. So why is this? And it's because of building codes. So Florida has a very strong building code, as you might expect. Without it, insurance would not be affordable for the average homeowner. And in fact, you may not know, but some of your home insurance here in Longmont is higher than it otherwise, well, it might be higher than it otherwise would be because we have to subsidize people in more exposed, vulnerable locations. Otherwise, they won't be able to pay for their own insurance. So it's a whole national, in fact, global system that averages out. So the question is, are these building codes effective against hurricanes? And is it cost effective? Is it worth our while to build or pay for a house that's built to code? So we looked at some loss data and some hurricane data, and there's no shortage of hurricane data in Florida. So you might remember in 2004, 2005, Florida was hit by 7 hurricanes, and the darker the reds here, the higher the losses from those hurricanes. So it was spread across the state, about 320,000 claims. So we looked at all those claims data, and I just wanted to point out that the damage patterns from hurricanes vary wildly from one hurricane to the next. So no 2 hurricanes are alike. So Charlie on the left was a category 4, but it was very small in size. And so it zipped across central Florida and made landfall near Tampa, and all the losses were confined to the track. That's that black line. Whereas on the right is Hurricane Francis. This was a very large, meandering, I think it was category 2 hurricane that caused losses across the entire state, but the magnitude of the losses was less. So anyway, we analyzed and crunched all this data, and the result is that, luckily, yes, indeed, the building code is effective. And in fact, for a house that's built to code, the losses are about 70% less than the losses if your house was not built to code. And it's cost-effective policy. So for every $1 you spend building to code, you can expect $4 back in mitigated losses. And if these hurricanes are going to become stronger in the future, then this cost-effectiveness is likely to go up. Now, it surprised me that only Florida has this strong building code. So other states prone to hurricanes like Texas, the building code is nowhere near as strong or well enforced. So this is a lesson that maybe other states could take up. Okay, so now I've said a lot about doom and gloom, everything getting more intense, so I wanted to leave you all with some hope. I was hopeful after I visited and testified to Congress and basically gave them the same message that we've been talking about here. And they were very engaged. It lasted 2.5 hours of questioning. Very informed, engaged response, so I was very pleased to see that. And it's not like we're flailing around in the dark, not knowing how to fix this. We've known for a long time how to fix this. That's basically by mitigating future warming and adapting to the warming that's already happened. So 2 ways we can fix this are to accelerate our transition to a clean energy economy. And it looks like that is happening because clean energy prices are plummeting. They're almost becoming somewhat affordable, widespread. And we need to accelerate our adaptation to the warming that's already happened. So there was a rather damning report that came out, I think 3 weeks ago, from the IPCC, the Intergovernmental Panel on Climate Change. The conclusion was that climate is changing faster than we are adapting to it. So if we don't accelerate, things are only going to the impacts are only going to become worse. And not only adapt, but adapt in a way that brings everyone up. So not just adaptations for the wealthy, but adaptations to people experiencing poverty as well. Not just leaving people out on the floodplain or in wind-prone regions, for example. Great, well that brings us to the end of the discussion. So I just wanted to summarize that hopefully I've motivated that we're in this new era of impacts from extreme weather. We can think of climate change as this pervasive and growing risk multiplier, and we're not in the dark here, we know how to fix this. So yeah, thanks for your engagement today, and thank you. I'll open it up to Q&A.
Thank you very much. Boulder County, 8 years ago, 9 years ago, experienced flood losses, more recently fire losses, and there are a number of other smaller fires. Recently, I became aware of the Boulder County Community Wildfire Plan. Longmont, as a community, was not a very apparent participant in this plan, although a number of the hot spots were identified in 2000 and 2011 in and around our community. Can you, you're gonna keep me up all night worrying about this, thank you. Is there a data source that is similar to the kinds of things you show globally and nationally that would help educate some of us about the losses and the risk that you show here for fire or flood, a place that we might go that either the insurance industry or other researchers have that might tell us more about our own community, Front Range or something. Thank you.
Yeah, thank you for your question. Yeah, I'm not terribly familiar with the plan, but thank you for educating us. I'm familiar with global loss data sets or loss data sets by state. I'm less familiar with loss data sets at the very local level. So I'm unable to point you to something. Yeah, I believe you remember I showed that map of the US states and the redder colors had the highest losses. That was NOAA's $1 billion loss database. If you go in there, you might be able to drill down more locally, but I'm not aware of a publicly available local data set. That's a good question.
This may not be your area of expertise, but the drought situation, especially how it's affecting Lake Powell and Lake Mead, and I know that you deal with insurance agencies or whatever, what would happen? I mean, as far as an insurance, or we all know what would happen, there would be an abandonment of cities and whatnot, but if Lake Powell does run out and there's no electricity, the water will be there, but they will not be able to funnel electricity to Vegas and Los Angeles and Phoenix and whatnot. Do your models study things like that? Do you have any kind of information?
Yeah, that's a great question. Yeah, water and energy are so interconnected, and I'm going to throw a third one in there, and that's food. So in the research and risk management communities, we talk about the water, energy, food nexus, this triangle. They're all very highly connected. And as you point out, as an extreme event can knock the whole thing out. Now, I mentioned these weather and climate models. You know, increasingly we're connecting or plugging those into energy models. And in fact, there's some climate models that are designed specifically to predict and forecast energy resources, which includes things like drought. And some of them are plugged into population models as well, where we study the relationships between population and climate. So if population suddenly redistributes globally, how would that impact the climate system? So I think this is cutting edge research, and you've hit on something that's a very active area because we know the vulnerability of it.
Sorry. Do you know where, is there a website or some place where we can look to follow those studies or that research?
Yes.
Besides NCAR?
Besides NCAR, yes. The Department of Energy is very active in this area. They have their own climate models coupled to the energy models, and they study this food, water, energy nexus. So off the top of my head, I'm sure there's some websites you can find on the Department of Energy website. Mm-hmm.
I've been learning recently that the carbon dioxide is about a 4% factor in geothermodynamics, and that water vapor and water is a 95% factor, and that the cooling of the planet from when it had no life to now has primarily been through pedogenesis, through the development of soil, and through green cover of the planet's surface that has kept the biosphere, or brought the biosphere to the livable condition that it's in. And that over the last 8,000 years, through the activities of humanity, we have lost about 40% of the green cover of the planet. And I'm wondering what, if anything, you guys are doing in researching and learning about how we can regreen, literally, the desertified portions of the planet that actually offer an opportunity through seeding cloud formation out of hazes and that kind of thing with the bacteria. And I'm just kind of wondering where you all are with that, it seems to me we really do have a chance in learning what we have learned over time about how all of this works. And through changing our practice of agriculture, we can actually cool the biosphere.
Yeah, another great question. I'm glad we're all thinking more broadly than just the atmosphere and the climate, because that's the direction that the science is going as well. It's a lot more interdisciplinary, as we call it, than it used to be. So atmospheric scientists, for the most part, no longer just study the atmosphere, they also study the interactions with things like the biosphere and agriculture. And just on that point, when I've been talking about the impacts of climate change, there are other anthropogenic impacts other than just warming the atmosphere, and that's changing the land surface, so that can really impact local climate. For example, increases in irrigation for agriculture can lead to localized cooling spots within an otherwise warming region, and it can change precipitation patterns. So again, I'm going to fall back to my point that we're still learning about these interactions and developing the technology to study these kinds of problems. This is, again, you're at the cutting edge there with these kind of questions.
Hi there. I have two main questions. My first one is, how do your models kind of consider that the sun is going into its grand solar minimum? And then my second one is, how has COVID impacted all of this? Has it accelerated? Like, what's the rate of change here?
Mm-hmm. Yeah, maybe I'll take the second one first. Some researchers at NCAR have studied the impact of COVID on climate. And I think the general takeaway, someone might correct me here, is that it was negligible. You saw those the rising carbon dioxide and the rising methane, so just a few % change in the increase in a single year or a couple of years really has negligible impact compared to that build-up over decades. So what would really have an impact in the Earth's temperature is to curtail that accumulating greenhouse gas and accumulating warming. So it's my understanding it's had minimal impact, regretfully. It needs to be a sustained effort. And the first question about the solar minimum. So are you referring to the sunspot cycle there? Yeah. So we do have a solar physics laboratory at NCAR. I don't know much about that. I study just the atmosphere. But yeah, I'm going to punt on that question. I'm not sure how that's coupled, but I would imagine it's included. I don't know that.
It basically affects the vegetative potential to capture solar energy. And with the sun's potential going lower, we could be, as some people are theorizing, that it could be a new solar ice age. So, not sure how those two kind of play with these models that you have here.
Yeah, again, I don't study that interaction, so I can't respond. Yeah, I'll have to get back to you after I ask my solar physics colleagues.
Does the insurance industry provide any incentives for mitigation or only for their losses?
So yeah, could answer that on a few levels. The entire insurance industry is very interested in adaptation. So that's things like people putting shutters on the windows to prevent hurricane wind damage, for example. I'm not sure they would reduce premium for mitigation. I'm not aware of that so much. It's more adaptation. Mm-hmm.
I saw something on public TV a while back that basically said the melting of the permafrost around the planet is such as a feedback loop going on. No matter what we do, we're hosed. There's so much methane is going to be given off by the frozen stuff in the permafrost. It's going to be released in billions of tons of methane, and no matter what we do, at least in the next couple of 100 years, we're hosed.
I might challenge you on being hosed, but certainly some additional warming is locked in because, our society is built on a fossil fuel energy economy. We're going to keep using it at least for many years to come as we start to transition. So there will be additional, what we call forcing for warming, and just the greenhouse gases that are already up there, all the methane that's already been released, and the CO2 that's already been released will stay there for many decades and continue to warm the planet. So yes, it will continue to warm. The actions we take today will pay dividends down the road, so even though we do expect more methane to be released, the amount of additional methane we can control. So, and we want to combine mitigation with the adaptation so we can become resilient to more intense precipitation and flooding and more intense hurricanes. So, yes, we have solutions, but it's going to be a rough ride, I think.
This is a micro question concerning the Marshall Fire. The NCAR has quite an array of wind sensors around the Front Range here. I don't know how many there are, 50 or 100 or maybe more. Has anybody done any studies about the wind fields that occurred during the fires and trying to do correlations on damage, risk control, risk management, things of this sort?
Yeah, so the winds during the Marshall Fire, they were nothing new. We're very familiar with these strong downslope windstorms that we get every winter, it was a very strong event, but it certainly wasn't record-breaking. What was interesting about this event is that we have the downslope winds coming down the Front Range, and then there was what's called a hydraulic jump. So you might have seen this in streams. Suddenly the water is laminar, and then it suddenly becomes turbulent at a critical point. So this is what happened in the downslope winds. They were 100 miles an hour, and then suddenly, say, in Broomfield, the winds dropped to almost zero, even though it was 100 miles an hour, just like 10 miles upstream. So it was a very complex wind event and very localized that unfortunately triggered the fire in the place that took it into Louisville and Superior. Yeah. So there's still lessons to be learned about this event and how it interacted with the dry vegetation.
I wanted to come back to the insurance question because I think we all know we have some sense of how to fix this. And I'm wondering, in your conversations with Congress and with your work with the insurance industry, is there something, I just feel like we do need to have people take responsibility for this. And the insurance industry seems like a key player here in encouraging legislation that would lead to more clean energy. I mean, we're rolling it out, but it has, bumps, and we take 2 steps forward, and then we, take another 3, 4 steps back. And I just feel like you might be in the right place to kind of have this conversation and urge insurance to not just, predict the future so they can raise rates, but to actually do something to urge our Congress to take action before this is too late.
Yeah, spot on. Well, the insurance industry doesn't need any persuading. They were the ones that came to me because they saw climate change writing on the wall. They knew it was happening, and they needed something to do. They need to do something about it, otherwise they're going to go under. So, and they are highly influential, and they use that influence across the whole world of finance. So they start initiatives to, for example, put a tax on any financial transaction, say in stocks and shares, and that tax would pay for mitigation measures, for example. And so they're trying to work out ways to finance climate change mitigation. So they are leading the field, and they're a lot more nimble than, say, federal governments that can take a long time to implement policies, whereas private industry can react and implement and test things and try things out, and they are very active in this space, so I think that's a reason for hope. They are leading the charge already.
I think we have time for about 2 more questions.
Hi, I just have a situation where I'm on the street corner at 6th and Main every Saturday with signs and whatever, and everyone just turns a blind eye. And you have to get government moving, and you have to get guys like Manchin, who drives a Maserati funded by the coal companies. Somebody has to stand up and say, this can't work anymore. And they just don't seem to do it. It's like, oh, this is peachy keen for me. We've got, I saw the fire devastation yesterday for the first time. And I mean, I used to work down that way or whatever, and it just brought tears to my eyes. And nobody's really talking about it. It's like, oh yeah, that happened, but let's go on. We have a war that's raging in Europe. What the hell is wrong? Go after these guys and say, you can't do this. This world can't survive. If you have children or grandchildren or great-grandchildren, what's going to be left? Everybody wants, I have $500 billion yacht that they're, confiscating, and I don't know what they're going to do with them. But, you know, it's like you have to draw a line sometime and say, this isn't going to work any longer. And, you know, Kathy and I are on the street corners or whatever with our signs, whatever it is. And there's a lot of support. And, you know, you'll get a big crisis or whatever going on. And you'll get people out there or whatever, and then it disappears. You know, so it's like, I don't know what the answer is. I thought, you know, the 70s in Vietnam was going to be my last marching in the streets. But, you know, you can't do it. If it's there, you have to do it.
Yeah, I hear you talking about communication. So there's a lot of social science research going into understanding exactly why people are not responding to the message. So I think you were asking, why aren't people reacting in the way I expect them to this kind of information? Yeah, so you might be familiar with the Yale 6 Americas study, where they categorize people's responses to climate change information. So at one end of the scale, one group of people are entirely dismissive, and at the other end of the scale, they're actively involved in climate mitigation and communication. And then there's a lot of middle categories. So a reason for hope is that the US population is shifting. There's been a shift over the past, even the most recent 5 years, away from dismissive towards engaged and actively involved in climate measures. So I'll leave you with that reason for hope.
Did you want to take one last question?
Sure.
I think we have one last question here.
Hi. I'm very interested in the carbon tax. And according to one of my friends, they already have a carbon tax in British Columbia. How do you think that we'll be able to talk enough people in America in order to enact a carbon tax, no matter how small? Because last time I checked, there was a huge amount of resistance to it.
Yeah, that is a tricky question. I think this comes back to my response earlier about taxing finance. There needs to be a way to fund these measures and to accelerate progress. The carbon tax is one way to do it, and I know it's problematic. But yeah, I haven't studied it in detail, and I'm not sure what the state of play is with the carbon tax, so I'll have to leave it there.
Let's thank NCAR and Dr. Dung for joining us. And thank you all for joining us here this evening. See you next time.
Yeah, thank you.